Hi everyone. Good morning and apologize for the delay. Just to start this webinar around hydrogen for heavy duty transport. My name is Ruben Pinedo. I'm one of the business innovation managers at Teesside University, and I have an engineering background with 20 years experience supporting SMEs to increase productivity and achieve energy efficiencies. To start this event, I would like to send a very big thank you to all of you attending today to this webinar, but especially to all the presenters here today that have made this event happen. So without them, that it won't be possible, and I'm sure they are going to provide a lot of value to all of you. So a big thank you to all of them. Before to start this presentation, let's go to start with a bit of the housekeeping, even if it's a webinar. So the first thing to mention, this session is being recorded, and the and the presentations will be available to all of you at the end of the event. It may take a couple of days. Please bear in mind that, as we may need to do some editing. You will be able to write your questions on the Q&A box. All of the questions are going to be answered at the end of all presentations by the panel. Okay. In case that you haven't used Teams before, please note that there are some couple of buttons that it can help you to be of support through the presentation. I'm not going to go through all that sessions, but probably to highlight a couple of the buttons that it can make that they are the most important ones. The Ask Questions, which is at the bottom, at the right button, and Ask My Questions on the top side, as you can see. The agenda for today. Okay, we have a quite extended and professional kind of agenda. You can see on the screen where we have 6 fantastic speakers from the industry that they are going to provide an insight of the use of hydrogen in heavy-duty transport. But before we start with the industrial presentations, I would like to introduce a bit about the Teesside University and the Teesside Valley Hydrogen Innovation Project that we are running at the university. So for those people who is not familiarized with the Teesside University is based in the northeast of UK in Europe, and it has 2 sites, one in Middlesbrough and another at Darlington, all of them from 16 miles from each other, but with different focus. One more on engineering business kind of focus, and the other one is focusing more on health and biology. The university has around 18,000 students across undergraduate and postgraduates, and employs about 2,500 staff. This it tries to represent is the vision and the mission statement of the university, with clear states that one of the main aims or mission is to make and support local economic and national economy and global economies in the areas of research enterprise to support local economies. The university has been recently restructured and counts with 5 schools supported with over 700 academics to deliver academic research and business activities. Today, we are representing the School of Computing, Engineering and Digital Technologies. Recently, the school has been restructured and has been merged, the School of Computing and Engineering, just to meet the current needs of the industry regarding to provide or equip future engineers with the computing skills demanded by the industry. In addition to the traditional academic services, In addition to the academic services, Teesside University offers a wide range of services to support industry to achieve their ambitions by providing access to talent in the form of graduates, internships, and placements. Access to academic knowledge in the form of consultancy, collaborative research projects, through a specialized funded innovations project as the one that this webinar is promoting. In that case, it's the TIS Hydrogen Innovation Project. Access also to very specialized laboratories in the areas of chemistry, biology, engineering, and computing. And as I will mention later on, the hydrogen lab that is in the process of being commissioning, but also in the development of supporting the accreditation and development of industrial and academic courses, including for online delivery. But not least, we have also a number of programs to specialize on connectivity to support, to put you in contact with the right organizations. One of the important things to bear in mind is that Teesside University is in the process of investing over 300 million in specialized facilities. This includes some of the recent announcements in the media that you may have heard from the Ben regarding the Hydrogen Transport Center that will focus in the development and testing of new hydrogen technologies for cars, trains, ships, and planes, but also a 14 million investment in the Tees Valley Net Zero Innovation Center that will focus on clean energy and decarbonization. In addition, Teesside University has launched recently other 5 new centers. This includes the National Horizon Center, that is a 20 million state-of-the-art chemical and biology facility, and the Industrial Decarbonization and Hydrogen Innovation Center that I will provide a further detail at the end of this presentation. On these screens, we're trying to display some of the programs that we are running at the Teesside University, and I apologize for the complexity. I don't think that is a very nice kind of a slide, but what we're trying here to depict or to illustrate is that the Teesside University is running a number of programs to support industry to achieve their ambitions. As you can see, this the university, we have almost a program for any size type of organization, any type of project that you have at any TRL level. So that it doesn't mean that you have contributed financially, but also we have free paid programs where you can contribute. So it's for almost any organization that they can jump in or decides to engage with the university at any level. So in green, it is highlighted the services offered through this specific project, that is a Valley Hydrogen Innovation Project that focuses on raising awareness about the hydrogen economy, creating new skills into this specific area, and supporting SMEs to transfer ideas into new products. So Teesside University is, as I mentioned before, in the mission and vision statement, Teesside University is committed to support industry in the transitioning to a more sustainable world. I think that most of you present here today will agree that the hydrogen economy is perceived as part of the future low carbon economy. There are several reasons why hydrogen has received, again, serious consideration as an alternative energy source, such as the global desire for more environmental friendly fuel sources, improvement in hydrogen technologies, increasing government support for climate-friendly fuel diversification, and changes in global energy policy in emissions standards. I mean, we have seen how very recently new taxes are coming to specific sectors where they are going to be badly hit, and therefore they need to start considering alternative fuels. However, hydrogen presents still a lot of challenges overall in some areas regarding safety, cost, infrastructure. I would say more than safety, cost, and infrastructure are the 2 more important ones. According to the Hydrogen Council, the international hydrogen market could be worth up to $2.5 trillion by 2050, meeting 18% of global energy demand and providing 30 million jobs around the world and reducing CO2 emissions by 6 gigatons per year. So this is quite a lot of consideration and a big market coming up that is going to develop. And I think this project, what it is trying here, and that's what it is the aim of this project, is to support industry to undertake this opportunity. As a result, Teesside University has launched this project and other number of initiatives to support local industry to engage in this emerging economy. So one of the programs, as I was saying, is this specific one, the Teesside Valley Hydrogen Innovation Project that aims to raise awareness of the hydrogen economy by providing free services to SMEs to develop new products and services. It's a fantastic opportunity for companies in the Teesside Valley region. This project is partly funded by European Regional Development Fund, and the project is going to start it in 2018 and is going to finish in 2023. However, even that is only for the Teesside Valley, that specific one, the Teesside Valley Hydrogen Project for the Teesside Valley area. We have other programs, okay, and other mechanisms that we can still support organizations across the country and globally. As mentioned before, an objective of this project is to raise awareness of the hydrogen economy and associated topic of interest to industry. To do so, we are delivering almost one webinar every 2 months on topics related of interest to industry in the context of hydrogen and decarbonization. We getting these webinars based on demand from industry, where we start thinking sectors that are more approaching to specific topics. So the next event will be in February, and that is as a result of coming quite a lot of organizations to us asking specific questions about how to pitch their ideas, where to go, different market strategies. So as a result, what we have decided to put is together this event where a startup and SMEs will have the opportunity to pitch hydrogen ideas in front of a specialized hydrogen panel form of investors, technology providers, and influential organizations. Other webinars planned later in the year will be around components to build hydrogen solutions and process simulation. If you are interested in presenting at a few webinars or you would like to hear more about them, please don't hesitate to contact me. The project, the Teesside Valley Hydrogen Project, okay, offers a minimum of 12 hours free support to any SMEs in the Teesside Valley area across any of the areas displayed in the screen. To date, we have assisted over 20 companies at different levels, and we have supported the development of a range of products and services. As part of the project, the team is working on the development of a new hydrogen technology aiming to reduce CO2 emissions and hydrogen production costs, as well as developing membrane technologies for hydrogen purification and CO2 capture. Today, you are going to hear about the use of hydrogen for transport. This is an area that the Teesside University has expertise, and through this project, we can contribute to accelerate the process of taking your products to the market. In order to support industry better and with experience over the years, we have developed a support model to support SMEs to achieve their ambitions and convert their ideas into commercial products. And you can see on the model, we have two different sections. On the top area represents the services offered through this project, the Teesside Valley Hydrogen Innovation Project, to convert ideas into proof of concepts. At the section below, what it tries to represent is how we can continue providing support to take your products or proof of concept all the way through commercialization. Each stage of this project and activities have an activity attached to it is to revise the project and to qualify to move to the next stage. Only projects involving the development of physical products and with quite clear route to commercialization may be eligible up to 2 weeks of free support to develop a lab scale prototype. We would like to offer further services to everyone, but we have limited capacities, and this program only allows us to support for a certain number of hours. What I would like to mention is that, and highlight, is that this is a regional development European fund, and the IP developed through this project will be held by the organization in its totality. Okay, so there is no university won't get any of the IP on that. I think that is important to remark that this project is not limited only to the capabilities and resources with the hydrogen team. We have also access as a wider range of expertise across the university in the areas related to digitalization, energy decarbonization, mechanical engineering, etc. On the left side, it is summarized the main capabilities that we have within the hydrogen team, but on the right side, you can also see other capabilities within the school. In that case, I have focused them more around the energy side, as I thought that it would be more relevant to today's topic. The project comes with dedicated chemistry and hydrogen laboratory labs that will be available to companies registered in the project. As part of the laboratory equipment, we are just working towards the development of a catalyst membrane reactor in collaboration with SMEs. So, as well as developing membranes technologies for a wide range of applications. In addition to the hydrogen lab, the project has access to other labs, including mechanical and digital laboratories, as well as manufacturing to support the development of a lab scale or other kind of pilots as necessary. These are, we're working with a number of projects currently. Some of them, they are focusing on the development of how to use hydrogen and ammonia to fuel ships. Other projects are looking about how to the excess of energy to be converted into hydrogen and to develop specific business models that it can catalyze that economy. Other projects, they focus around the development of specific hydrogen safety systems and smart hydrogen safety systems for different applications, educational and industrial markets. But last one and not least one, I think is important, is we supporting industry in the development of very specific kind of training for industry and education. If you remember before, I was mentioning that we have two models. The top part is what we have covered up to now. At the bottom one is the mechanisms that we can help companies to access further funding. So very briefly, I would like you to introduce the Industrial Decarbonization and Hydrogen Innovation Center, which is one of the 3 centers recently developed in collaboration with TWI. If you remember in the previous model, as I was saying, that the top part was focused on companies to transform ideas into concepts. This specific part is to support companies to bring the products all the way towards commercialization. The 3 centers have a common goals, and is to help business to realize their ambitions by accessing public funding to develop new industrial technologies and solutions through collaborative projects. The centers provide a center for industry to get awareness of public funding available and get support to transform conceptual ideas into winner bids. As part of the services that we offering through the centers, it includes a consultancy team that will discuss your conceptual idea and identify suitable open calls that the ideas can be put towards it. The Centre will also coordinate the whole bidding process, including the process for building international consortiums and the bid writing. The Centre focuses on the development of cost-effective low-carbon technologies to support industry drive for clean energy growth. The Centre will help companies to reduce their environmental impact and embrace successful new fuel and emerging technologies. This program they focus overall, not exclusively, for projects with TRL from 1 to 6. The Centre will look into 7 core areas of knowledge required to drive energy transition, create value, and make a positive impact towards decarbonization strategy across sectors. This includes fuel cells development, material technologies, energy digital solutions, hydrogen technology, social science, and storage technologies. If you want to find any more about how to engage on these programs, in any of these programs, please don't hesitate to contact me, and here are my details for further questioning. So this is all from the Teesside and the Teesside hydrogen perspective, and I would like to introduce the next presentation from KTN on Knowledge Transfer Network, and I would like to introduce Simon Buckley. Simon is the Knowledge Transfer Manager for Low Emissions Mobility at KTN, with 10 years of experience in developing electric and hybrid vehicle technology and energy storage systems within the innovation sector, and has worked on a numerous APC, Innovate, and H2020 programs. All over to you, Simon, and thank you for joining us today.
So yeah, thanks so much, Ruben, for the introduction, and thanks for the opportunity to speak today. So as you mentioned, I'm from the KTN. I look after low emission mobility, which is a very innovative topic at the moment. We need to be innovative within it to reach our carbon targets. So I'll give you a little very quick run through where the KTN sits within the Innovate UK family. And as you can see, we've got BAYS, we've got UK Research, UKRI, and Innovation. We've got Innovate UK, we've got KTN, we've got Enterprise Europe Network, and we've also got the catapults. We all perform a valuable function within the innovation ecosystem, and we're all there to support companies at various stages in their life cycle. What we do, we exist to connect innovators with a variety of different funding, different partners, and we also provide deep expertise to help you make decisions about whether you should go into, so there might be opportunities in different sectors, or we might be able to help you access grant funding, or we might be able to connect you to a suitable OEM, for instance, who can help take your technology to the next level. We have two kind of main aims. One is obviously we need to bring economic wealth and increase GDP to the UK. The other is net zero. So net zero, I think, is increasingly in people's faces, as it were. It's increasingly on the national news. We need to make changes now, and that is the heart of what we're trying to do. We're trying to accelerate that growth. This is just a wider picture of the hydrogen landscape, and you've seen a lot of stuff about hydrogen recently. It's obviously been around for a while, and it's going to be a key part of how we meet net zero by 2050, but also I think how we meet the carbon reduction of 68% overall since 1990 by 2030. And you have a various, you've got the Aerospace Technology Institute, you've got the Advanced Propulsion Centre, you've got the catapults, you've got the 3 government departments. So you've got departments for BAYS, you've got DFT, and you've got OZEV, who are all hydrogen is central to some of their policies. What we do and how we typically interact with companies is you would give me a call or drop me an email. We would sort out the time to speak, and then I would just have a chat with you, probably for about half an hour, to discuss how best we could advance your technology or what you're trying to do. And then I might even point you towards some funding or some local funding or local support, like this great initiative we've got here. Or I'd say, have you thought about this different sector? Or I'd connect you to different people or different partners who might be able to help you take your idea to the next level. Again, with the grant aspect, if I did point you towards a grant, we can also offer a light touch review service of that grant, and that can be on top of, say, any bid writing services. So you could get a bid writer, you could through this Teesside initiative, but then you could actually use us as well to give you a bit of clarity and technical expertise in some of the core points. So now I'll just talk a bit more about hydrogen and hydrogen for the heavy duty sector. So why hydrogen? So if you can see this, it's a very interesting graph, and I always like to show this. Since 1990, overall carbon emissions from vehicles have only come down by 3%. Now, we've obviously got much more ambitious targets and we need to hit them, and we have to work out a way to do that. You can kind of see that cars, although they've got better and they're not emitting as much carbon as they used to, there are a lot more of them on the road. So actually that stayed statically the same. It's the same across most areas. One interesting area here is heavy good vehicles, which is the second largest carbon emitter from a transport perspective. Now, heavy good vehicles are hard to decarbonize because the nature of their duty cycle. And this is where one of the reasons where hydrogen can play a really important part. I think there are also great opportunities in, say, shipping, ports, rail, and you're going to hear some great presentations today from innovators who have actually employed and integrated hydrogen systems onto vehicles to enable reduction of carbon emissions. So the hydrogen landscape, it's a very busy landscape, and there's a load of different production processes, which is not the focus of today, but you need to be aware of them, because where the hydrogen comes from is incredibly important for how much of a carbon impact it has. You then have to get that hydrogen to the point of use, and again, with carbon impact and actually from a use point of view, that's incredibly important. And finally, you've got the actual use. So how do we use that hydrogen? There's some core areas. I think typically hydrogen will be used for things like HGVs or ports, where it's actually quite hard to deliver that benefit with a battery vehicle. It's very difficult to imagine a battery HGV traveling from London to Edinburgh, for instance. It's a very long way, so you need maybe a quicker way to power that. Or at a port, for instance, you have ships with huge energy requirements, and the charge rates would be very difficult to achieve via battery. It would be very difficult to provide the infrastructure. So there's some interesting opportunities there. Construction's another one which is very interesting. You're going to typically, it might not have electrical infrastructure there, so how are you going to refuel and charge that vehicle? So there are a number of really interesting use studies that I think we all need to be aware of. So as you can see, it's a complicated landscape. So what we at KTN have tried to do is we are launching an innovation network, which is going to bring up and tie up various different enterprises in different areas. So like obviously Tees, but down in the southwest, and in Wales, southwest Wales, there's projects going on there. There's projects going on all around the country, as you can see from this map. We're trying to connect that, bring that expertise and join it up. And we're kind of agnostic, so we're non-competitive. So we want to have a non-competitive advisory group. We want to pool knowledge from all these communities around the UK, and make sure that knowledge is shared and allows local areas to have uptake of clean hydrogen at the scale and cost, and end users is going to be a big thing for us. So our focus is going to be around looking at the strengths and weaknesses of the UK capability, looking at those and looking at those emerging sectors. We want to provide a validated viewpoint on the innovation challenges that are holding back deployment and adoption in emerging markets and sectors. So I know obviously Ruben mentioned cost and infrastructure, definitely two of the big ones out there. How can we help that? And then we want to look at actually picking particular areas within a local region, saying this is how we can actually help that. And then we have a process for doing that to allow SMEs to get involved and provide solutions to those problems. We have a launch event for this and would really welcome and love you to join. So I'll probably put a link in the chat because you won't be able to click on that. But it's on the 12th of January at 10 AM. Where we'll be officially launching it. We'll have some exciting speakers from across the innovation landscape and government landscape, and you can then join and get used to get all the benefits of this network. And then just within this network, some of the end users and innovation projects going on may be along the likes of some of these pictures. So Zero Avia, for instance, launched the first zero emission hydrogen flight back in the summer. We've got, I know we're talking about trains later. There's ferries, there's ports, there's HGVs, there's gritters, there's buses. There's a whole range of heavy duty transport that needs hydrogen to decarbonise. One of the areas we discussed is ports. We've also got an innovation network around ports, and that is because there's a lot of each port now has to release a air quality strategy and how they're going to reduce emissions. Certainly the ports in England above a certain tonnage do, and to tie in with that and enable that, we're going to actually target what are the agreed cross-sector challenges within those ports, what solutions are out there, and what is the industry and government, are they aligned, can we make them aligned? So that's also well underway actually, and you can sign up again on that link to that one. I think it's got a lot of parallels and links with hydrogen, so please ask me any questions about that. I think we also need to look at Europe from a hydrogen perspective. They've put a lot of money into it, and some of the big projects, so H2 Hull runs from 2019 to 2024 to design, build and run 16 fuel cell vehicles, and they'll be up to 44 tons. I think some of the technical challenges will include cost and life cycle of the fuel cells, for instance, and I think there's a real opportunity to innovate within some of that space to provide solutions to some of these bigger OEMs and bigger players. From a funding perspective, I've given you 2 links here that you can click on. You can sign up to various newsletters, and that gives you an idea of how you might be able to access funding for some of your ideas. You can always talk to us, of course, or to Teesside University about potential options out there. So thank you very much for your time, and I'll be around later for the Q&A, so please let me know if you've got any questions.
Dr. Penkate Krusane is a chemical engineer with many years of experience working in industry, in R&D and product development in areas of chemical engineering, catalysis and reaction engineering, solid state electrochemistry with a special focus on solid oxide fuel cells, process design and ceramics processing. He's currently working on the submission of several Innovate and H2020 programs and has experience delivering H2020 projects. All over to you, Venkat.
Good morning to everybody, and thank you very much for your previous presentation, Simon, from KTN. That was very good, and I'm going to expound on some of the thoughts that you mentioned about the impracticable batteries for very large heavy vehicles, and I have a couple of what's called the back of the envelope calculations to share with everybody. So I'll talk a little bit about of course we are all trying our level best to participate in controlling the global warming to a rate of no more than 1.5 degrees C per year as mandated by the Paris Agreement and as mandated by the protocols in UK, which has the ambitious plan of lowering the global or rather completely eliminating the greenhouse gas emissions to zero by 2050. We all are very well aware of the fact that all our greenhouse emissions are coming from any or pretty much all these following sectors: transportation, power, chemicals, refinery, iron and steel, cement. We have discussed some of these issues in previous webinars as well, and today we will put a little bit more of focus on heavy duty transportation, and I will start by generally re-emphasizing the fact that Simon mentioned, that heavy duty vehicles cannot be decarbonized easily, and I say this relatively in comparison to light vehicles. Light vehicles appear to be moving in the general direction, particularly in the urban environment. Light duty vehicles can be charged somewhat easily. Battery power is increasing in its acceptance, and so there seems to be some sort of a solution for lighter vehicles. Unfortunately, the same solution does not exist very easily for heavy duty vehicles, and I will discuss some of those things. Of course, there's no need to re-emphasize this fact. Heavy vehicles mostly running on diesel locomotives as well, and we all know the damages that can be done in terms of having fuels like diesel, not only in terms of global warming, but in terms of emissions and in terms of the availability over a long period of time. So these are very critical constraints that lead us to slowly think about other alternatives. Battery power. Yes, we are aware of battery power. We all know about it. There's a lot of publicity about this, and a lot of people, in fact, even seem to think that batteries will be the be-all and end-all for everything. So, and that is one of those things that needs to be tackled in the form of an information campaign. And we have to be very practical in terms of understanding where batteries fit in and where other technologies fit in. So, keeping this in mind, fuel cells for transportation. I mean, fuel cells for transportation have been around for a little while, but I think at the end of the day, we are primarily limited by it's pretty well known, and I'll get back to that in a couple of minutes. Just for people, just a bit of a refresher. I think by now most people know pretty much what a fuel cell is. And there are different types of fuel cells. I'm only going to talk here a little bit about the hydrogen fuel cells, which is a low temperature polymer electrolyte membrane, PEM fuel cells, which finds widespread application in transportation because it can start up very quickly and it's a low temperature device. So essentially you've got hydrogen and you've got air on either electrode, and you have the electrochemical oxidation of hydrogen to give you nothing but water. So the important thing to bear in mind is that this is not limited with the Carnot cycle, unlike all our existing thermomechanical heat engines, and therefore efficiencies are very high. That's the well-known truth about a fuel cell. And if you compare the fuel cell with the battery, essentially these are the standard stuff. Most of us know about it, but what we really need to focus is the middle point, the fact that the batteries constantly needs. Every now and then, I mean, once the cycle is over, we need to recharge them, whereas a fuel cell can run indefinitely when the fuel is available. So all you need is fuel storage. So it's a matter of storing fuel and providing the chemical energy. And here it's the matter of charging the entire battery, which is a much slower process. It's a fact of life. It's a much slower process. Whereas filling a tank with a fuel is a very easy, facile thing to do. The other thing that people must realize is the fuel cell, once it runs in reverse, can basically electrolyze water to produce hydrogen. So essentially, it runs forwards and backwards as well. In the galvanic mode, whereby it produces electrical power and as a fuel cell, and in the electrolytic mode, when it uses electricity to produce hydrogen, which can be stored for reuse later. So there are a lot of enormous flexibility associated with fuel cells, and which obviously then if fuel cells are so good, where's the problem? And obviously they will come to that, and problem is obviously associated with transportation and storage. But let me just talk for 2 or 3 minutes about this battery power versus fuel cell systems. Batteries have been shown to work well with small vehicles, and the original battery hybrids, which were in circulation and are still in circulation right now, which are of the class of what is called PHEVs, plug-in hybrid electric vehicles. They essentially have a fuel tank and working in tandem with the battery. So they're basically hybrid gasoline battery engines. And now the transition is being made to battery electric vehicles, the EVs. Now, alternatively, what fuel cell electric vehicles will do is we have fuel cells and batteries in tandem. And it's just a matter of deciding which one is bigger. If you've got battery electric vehicles with a little bit of fuel cell, with a small fuel cell power, then we call that a range extender. Essentially, the fuel cell is being used as a range extender. Alternatively, you can have a battery for broad basic applications, which basically includes startup, acceleration, stopping, and so on. And most of long distance driving, cruise control can be handled by the fuel cell itself. And simultaneously, the fuel cells have a tendency to they'll have the opportunity to charge the battery while the process is going on. So you don't really need external charging stations. So that is the other thing. Now let us talk to the main issue, address the main issue about heavy vehicles. Can heavy vehicles work well with batteries alone? What is the issue with respect to size and charging? Let me give you an example. For example, and I picked it up from some truck companies like Nikola trucks and so on. They're out there. They're trying to make these hybrid FCEVs for their trucks. And many of these trucks, if you're talking about a driving range of 500 miles, as an example, will require almost 1100 kilowatt hour battery. Obviously, that brings into focus the charging rate of such batteries. What are the battery chargers around us? We've got 3 kilowatt chargers, we've got 7 kilowatt chargers. We even have 22 kilowatt chargers apparently, and even higher superchargers are already out there, and so it is claimed. But one has to bear in mind that once we go to 22 kilowatt and so on, we are talking about 3-phase power systems. We're talking about, and most of us electrical engineers would know very well. Three-phase power system would entail something of the tune of 400, 415 volts of power, and you'll probably be dealing with 30, 32 amps of current. And these things are not generally available. You can't use them on a regular basis. So obviously they're very, very specialized applications. And so let us say we have some of these advanced superchargers, and let's take a look at typical rates of charging. A small car, one of Tesla's models, which is about 75 kilowatt hour, with a 3 kilowatt charger takes 21 hours. The same car can be charged in 5 hours with a 22 kilowatt charger. So with all that stuff, we are talking about at least 5 or 6 hours of charging. So there's a problem. And the problem magnifies once you think in terms of charging 600 to 700 kilowatt hours, which is almost 60 to 70% of a battery powered truck. Assuming that you don't charge a truck from even 0 to 1100. I mean, nobody charges from 0 to the final value. Everybody usually charges 60 to 70% of the load. So if you were to do that, you're talking several hours. You're talking several hours. You're talking minimum 8 or 10 or 15 hours. We can sit and do these calculations in great details, but this is simply very, very impracticable. And then comes the cost. Some people will start talking about the cost. They will say that hydrogen is still available, which is pretty expensive. Green hydrogen is pretty expensive. So yes, okay, fine. Green hydrogen is expensive. Let's do the costs here. This is a case study for electricity for California, and you take something to the tune of about 15 cents per kilowatt hour. And if you were to charge that full BEV truck, 1100 kilowatt hours of charging, and you do the mathematics here, and then you get $165 that you're spending every 500 miles of charging. Then you take the next case, the same type of truck. Let's say it runs for 500 miles. And you now have an FCEV, and you look at it. Even if you were to take $3 per kg of hydrogen, let us say that is the upper bound of the green hydrogen cost. Compare it with 1 to 150 for hydrogen, which is the gray hydrogen via steam reformation. That is the lower end of the cost, which doesn't take into account any form of carbon capture. So 500 miles, 8 miles per gallon is generally accepted range. 8 miles, sorry, not gallon, 8 miles per kg of hydrogen generally accepted as a range for the truck. You take that into account, 62.5 kilograms per filling. That means 62.5 kilograms of hydrogen are used for 500 miles, every 500 miles of usage, and $3 a kg. You're talking about 187, and you compare that with 165. So we're not very far away. And when I say 15 cents per kilowatt hour, I'm being generous with the electricity, and I'm being a little hawkish in terms of hydrogen here, because the price of hydrogen is expected to come down. There are a lot of analytical data out there which talk about the lowering of hydrogen cost to almost $2 a kg by 2030. So, and then finally, if you are taking the hypothetical case of the cost of hydrogen to go down approximately comparable levels to the cost of gray hydrogen, which is $1.50 per kg, that could give you $94 every time you charge a FCEV after running 500 miles. So from an economics perspective, cost of refueling of hydrogen. Okay. Hello.
Sorry, my apologies. We just lost you.
Oh, okay. Can you see my screen now? Okay. Now can I repeat the last slide?
Yeah, I would suggest you do. Yes, please.
Okay. So I was at this point of making a very small back of the envelope economics calculation. And I went through this whole idea that if you were to bring down the cost of hydrogen to comparable levels to what a blue hydrogen would cost you, or the gray hydrogen would cost you, something of the tune of $1.50 or something, then this should give you a much lower cost of charging, as far as in terms of mileage. So from an economics point of view, the cost of refueling of hydrogen is very much comparable, but it's far more convenient because it's just a matter of 15 minutes. So what are the challenges? The challenges are still there as far as hydrogen supply chain is concerned. And we have a majority of hydrogen which are being produced by fossil fuels, releasing a considerable amount of greenhouse gas emissions. But if we were to engage in carbon capture, we still have the problem of transportation of hydrogen in pipelines over distances. So this is still work in progress. Renewably produced hydrogen is obviously still expensive, nevertheless, but it seems to be the best way of proliferating hydrogen refueling stations. You just take water and you construct a small refueling station and you locally produce hydrogen, and that's the best way to do things right now. And if you really want to propagate a hydrogen economy, renewable powered fuel stations of small capacity would be the best way to go. So that appears to be the thing, and I pretty much that's what I wanted to say. And before I just sign off, I will just talk to you a little bit for about 30 seconds about TU's commitment to hydrogen. Although Ruben has done a great job already discussing that. This is our new lab. Our focus right now is on steam methane reforming concept and evolving it to a higher level of sophistication and more efficiency by using catalytic membranes. But in addition to that, we have very much a strong interest in hydrogen production, hydrogen storage and transportation by using various other methods. So we are building our capacity and capabilities towards electrochemistry as well. And this Ruben has already put this up for you. And I would just like to summarize by saying that, yes, lower cost of power is and aided with a greater proportion of renewables can facilitate both battery use and hydrogen usage. It helps lower the cost of both, number one. Battery usage is okay for small vehicles operating within the city. There seems to be some sort of an understanding which has been reached and some sort of a method which seems to work at small 3 to 7 kilowatt charging stations. Heavy duty vehicles driving range greater than 300 miles will have battery capacities of over 800 kilowatt an hour. Charging times and charging rates will be extreme. It could cause materials degradation, so it's not a good idea, and I don't see any easy solutions for that. So therefore, hydrogen FCEVs with heavy duty vehicles which have onboard charging, essentially by using stored hydrogen, and stored hydrogen technology is available to you. So it is still a good option, and it's still the way to go. And one best way to do is to go for electrolyzers, which are well distributed in the form of small refueling stations. So I'll probably stop there and thank everybody from the ERDF as well as my technical team. Thank you.
Thank you, Venkat. That has been an excellent presentation. I see a few questions on the chat that we'll be able to answer later on the day. But now I'm going to first introduce Hyster, Lawrence van der Rijt, that is here today, but unfortunately we had a few technical problems at the moment, and he won't be to deliver this presentation live. However, he has just provided us with a record session that I'm going to play in a second. But just to give a bit of background about Lawrence. Lawrence graduated as electrical engineer in 1991 from the University of Den Bosch in Netherlands. He's a project applications engineer for Hyster-Yale Group in the Big Group facility in Nijmegen, the Netherlands. And the projects he's involved in are port and terminal applications and zero emissions big truck development, which is closely related. Now, as again, Lawrence, a big apologize, for the technical problems that we have incurring today, but hopefully, the audience will benefit from this recorded version. If you have any questions, he's here in the audience today. Please keep posting the questions, and we'll be able to send it by email to him, and he will try to reply them as better as he can. Okay, so with further delays.
Good day. My name is Laurens van der Rijt, and today I would like to talk to you about the development of zero-emission big trucks. Looking at the Hyster product range, you can see that we have an extensive offering in electric counterbalance and warehouse equipment trucks. However, this is significantly different from developing electric big trucks. The main difference is in the power required to operate the truck. and developing such big trucks based on conventional voltages, 80 volts, 120 volts, would lead to excessive currents. And high currents is a nasty thing. It develops heat and it requires very thick cables with large bending radius that are difficult to implement in the frame of a truck. Therefore, we decided to develop this range of trucks based on high voltage technology, which will keep the current requirement to a minimum. Conventional trucks have some 800 liters of diesel on board, and this represents a certain amount of energy, almost 8,000 kilowatt hours. Now, trying to pack 8,000 kilowatt hours of energy into a lithium-ion battery pack would result in a battery pack that is about 60 cubic meters in size and weighs close to 100 tons, which is operationally not feasible. Similarly, replacing that diesel by hydrogen requires some 230 kilos of hydrogen to be on board, and even when compressed to 700 bars, that leads to a volume that is not sustainable on the truck. This almost 6 cubic meters is the gas volume, and the tanks would have to be around that, would be even bigger. Simply not possible to integrate in the frame of an existing truck. So what do we need? We need application-specific truck configurations and an intelligent design that optimizes the whole truck performance. And we need smart energy recovery to maximize the efficiency of the truck. Improving the efficiency of the operation is done in two separate methods. One is a fairly conventional braking energy recovery system, and as you can imagine, a vehicle weighing 80 tons with a 40-ton container in the spreader traveling at 23 kilometers an hour generates quite a lot of energy when being stopped. The second system is a whole different system. As you can imagine, when the container is brought up, that is done by the battery powering pumps, taking hydraulic oil from the tank, pushing that into the cylinder so that the load goes up. When coming down, the oil is flowing back through the pumps back into the hydraulic tank. And this oil flow makes the pumps run, working as generators, powering back into the lithium-ion battery. This is a system that will be patented by us. So all of that has led to such a truck as you see on the screen right now. This is a fully battery electric top loader, laden container handler, and I'm not sure if you can hear the noise that this produces, but as you can hear, the sound of setting the container down on the ground is considerably louder than the sound produced by the truck driving and hoisting. So looking at the performance of this truck, we have come to 3 or actually 2 operational models. On the left hand side and in the middle you see a truck fitted with lithium-ion batteries, and with either conventional charging or including opportunity charging, we believe that we can cover a low to medium duty cycle. In case of a heavy duty cycle, however, this will not suffice and additional power is needed, and this can be done in the form of replacing part of the battery with hydrogen tanks and fuel cell systems. Imagine a truck needing an average of about 70 kilowatt hours per hour. Starting off with a full truck, after the first hour 70 kilowatt hours of energy is expended, after the second hour 140, 210 and so on. Going down to about 7 hours of operation when the battery needs to be recharged. And in this example we are assuming a charging power of 420 kilowatt hours to be put back into the truck in 1 hour. That allows the truck to go into a second shift and after repetition into a third shift. That is graphically represented on the left, where you see the state of charging, the state of charge of the battery diminish, and then where the green block is representing a charging boost to bring it back up. The second shift, the third shift, and this just continues. Depending on the charging rate, depending on the operational use, this is actually feasible for a truck. It creates quite a big peak draw on the net, but it's possible to do that. The black line in the top is the state of charge of the battery pack when a fuel cell range extender is used. And this fuel cell keeps the battery charged to a maximum all throughout the operation. Also, it means that the swing on the state of charge of the battery is far less, which leads to a healthier battery state of health. As I said before, with one truck it's actually feasible to employ this charging pattern. Now imagine charging a fleet of 20 trucks. What you would need is a very strict operational planning describing when each of the trucks can be connected to the charger. And when an operational planning is worked out, as in this example, it creates a draw on the net that is actually fairly constant and very well manageable. However, if it's operationally not feasible to run these trucks in a manner that allows them to go to the charger at their designed time, at their assigned time, you will create a load that looks like this, with higher peak demands on the grid, with gaps in the operational use of the charger infrastructure. In case it goes really bad, you create an enormous draw, a peak on the grid, and this is a situation where the lamps in the town will go out. That is why we believe that for heavy-duty applications, for the use of such equipment in a fleet of trucks, it is only feasible to do this with a hydrogen fuel cell range extender on the truck. Looking at the customer side of things, there are infrastructure requirements to be contemplated. In case of operation of an electric truck, one of the first things that has to be considered is the main grid capacity, and that includes the infrastructure on the terminal. And if that is deemed to be insufficient, there may be significant initial investments needed to bring that up to speed to be able to operate such a truck. This will lead to higher operational cost, and as we have seen, it requires a complex operational planning. Of course, when using hydrogen powered trucks, there is also infrastructure to be taken into account. What will be needed is a filling station. That can be a mobile unit, depending on the size of the fleet and the hydrogen requirements. It is possible to set that up. Ultimately, and this would require a larger hydrogen demand, it is possible to create hydrogen generation on site. using perhaps green power from solar panels and wind energy to have your own electrolyzer at the terminal. So where does this lead us for now? Well, besides the electric top loader that you saw in the movie earlier, we have continued to develop a top loader with the system that I described before, a smaller battery and a hydrogen onboard tank system that is powering a fuel cell that continuously recharges the battery. This truck has been built and is currently in test in our test center. And ongoing developments have created the design for a fuel cell reach stacker. And that truck will be deployed at the port of Valencia in Spain as of next year. Looking further, we are currently engaged with about 12 terminals globally, looking to see how we can implement such ongoing developments in trucks with funded projects. And of course, our capacity in this is not unlimited. We need to determine which projects are feasible to be pursued. That means that we and the terminal operator need to determine which terminal, which project may be suitable. And that depends on the location, on the funding available, on the infrastructure, on local support, and on truck requirements. That concludes my presentation for today. Thank you for your attention, and if there are any questions, I will be happy to answer these.
We are going to pass to our next presentation delivered by the ULEMCo. So our next speaker is Amanda Line. Amanda has over 15 years experience in the hydrogen industry, having previously founded the fuel cell company Ecal Energy, and through her consultancy business Burgundy Gold Ltd. She is a specialist in the commercialization of clean technology, and she has been a director of the Liverpool City Region Lab and is chair of a UKFCA. So all to you, Amanda, and thank you for coming today.
Thank you for that introduction. Yeah, I'm going to provide, for those of you that haven't heard our story before, I'm going to provide you with information about a technology based on hydrogen dual fuel that we have on the roads across the whole of the UK, and in fact some vehicles in Canada and Switzerland. And the vehicles that we're focused on that can give an immediate use of hydrogen in any location today, based around providing baseload volume for that hydrogen infrastructure. So just a bit of an introduction about ULEMCo and what we actually can do both now and then are doing in the longer term. So in the short term and immediate availability, we have a technology that enables any diesel vehicle to use hydrogen, so become a hydrogen ready or a hydrogen enabled vehicle. I'll provide a little bit more information about that. However, in that process, the amount of hydrogen that the vehicle uses provides an immediate CO2 reduction as far as tailpipe is concerned, linked to the volume of energy that we replace from the diesel use with the hydrogen. And that, as I said, is available now. Longer term, our company is working on 100% hydrogen versions, whether that's fuel cell or more likely combustion technology, where by using 100% hydrogen, we can have zero emission vehicles as described previously that provide convenient and practical ways of delivering zero emission. So our hydrogen dual fuel technology is arguably the cheapest way that you could do today to reduce carbon emissions on a vehicle, or certainly using hydrogen on a vehicle. And by that, the technology is the cost involved is taking an existing vehicle and adding hydrogen equipment that enables the vehicle to then operate with hydrogen. The best results that we've seen have particularly worked well based on back-to-base duty cycles, principally because that enables the vehicle to provide baseload for large-scale hydrogen vehicle refueling infrastructure. We have also shown that in the urban vehicle cycles, we can also improve on Euro 6 diesel air quality emissions, so we're ticking both boxes required for customers in the area. As I said, the technology is available now, and because it's based on combustion technology, the maintenance, management and use of the vehicle is very similar to the way diesel vehicles are operated, so there's no requirement for the operator to change their duty cycle other than to make sure that they fill up with hydrogen. In reality, we're adding extra energy on board the vehicle. We don't alter the diesel vehicle tank system in most cases, and therefore actually there is no range anxiety, because if there's no hydrogen available, the vehicle can use the diesel to perform the rest of its duties, which is really important because that addresses a current barrier for anyone in a real world use looking to utilise their vehicles for the job that they're employed by, not for saving carbon emissions. So the first step we take in the technology is to understand the duty cycle of the vehicle and determine how much hydrogen is both necessary and possible to fit on board. The less hydrogen tanks we need to deploy, the cheaper the technology solution. The process to do that is for us to look at what does the vehicle do in its normal diesel use and assess what space there is in terms of packaging to put on, and therefore how we would optimise the percentage of hydrogen displacing diesel to facilitate at least a minimum of a daily fill. The vehicle that you can see on your right hand side is the one that's been deployed in Switzerland. If we've done the vehicle before, which these days we've done quite a few, there's rarely there isn't necessarily any bespoke engineering. However, we provide the capability to do that so that we can install that onto a single vehicle, and we also have a specific piece of work that we can do to look at the duty cycle, whether that's gathering data beforehand and afterwards to optimise the percentage of hydrogen that's involved. The vehicles are supplied post-registration conversions with a vehicle special order that we run through with the VCA so that the vehicle can operate safely and legally on the road. In a bit more detail, the picture on your right is a 74 litre tank solution that we've deployed on a Dennis Eagle refuse truck. Three 74 litre tanks represent about 5 kilos of onboard hydrogen, and in typical refuse truck duty cycles across the UK, based on displacing about 30% of the energy coming from hydrogen, that vehicle will use just less than 5 kilos a day and be able to provide that as a base load for the infrastructure at a back-to-base depot. So if you can imagine a fleet of refuse trucks at any typical council, between 30 or 40 vehicles may be operating out of a single location. All of those vehicles can be hydrogen enabled and use around 5 kilos a day, depending on their duty cycle, will give you a base load for a 200 kilo a day type station. The vehicle you see in front is a further example. If you look at the middle between the cab and the tank, you can see where we've installed a single 205 litre tank. The process involves us doing some once an order is placed, there's a lead time of around 4 months to order the long lead time components. Then we need about a month or so to complete any other engineering design. The vehicle itself only needs to be off the road for a maximum of 2 weeks. In fact, the vehicle in front of you that was converted during the shutdown, COVID shutdown earlier on this year, was actually in and out in a week. And as I said, we've deployed the technology to date in a range of vehicles focused on commercial applications in 3.5 tonne vans upwards. The most sort of logical, sensible and cost-effective way to provide the baseload is to focus on the heavier duty end, but we have a number of customers in the large van area where they use other energy on board the vehicle than just driving the vehicle, and in those circumstances the alternative battery technology will never make sense because they can never do the onboard load that they need, or for that matter the range that they would require. So consider things like longer ranges for the refrigerated van that you can see there for Ocado. Ocado are implementing some electric vehicle applications, but they're very aware that those really only generally apply in the London area. So consider if you took 100 of the urban trucks, urban trucks located around a single back to base location. So here you could be talking more than 200 kilos a day at a location, but you could imagine that those are a base load on refuse trucks for a council, plus suburban delivery vehicles. The supermarkets tend to have locations where they distribute 200 to 300 miles, less than 200 miles a day from a central point. In that circumstance, we've demonstrated that you can save, based on the use of hydrogen, at least 2.6 tonnes of CO2, particularly based on green hydrogen. And in that particular duty cycle, the vehicles will not, even though they're Euro 6 vehicles and therefore ultra low emission as far as air quality is concerned, the technology would also further reduce NOx. And that latter point has been verified through our involvement in the low emission freight trial, where we did a whole range of vehicles. The purpose of the project was to show the flexibility of the technology so that at any one particular location there will be sufficient ways to provide baseload for hydrogen refueling. And a number of the vehicles completed full emissions tests done at Millbrook, where in the R&D sense, different vehicles up to 60% in the case of one of the vans. The biggest single issue actually in a practical sense for anybody deploying hydrogen vehicles today is the fact that actually the hydrogen infrastructure is either not available, and if it is often unreliable. It is really important to understand that if you're going to embark on investing in hydrogen infrastructure, you need vehicles to use the filling station, otherwise they become extremely unreliable. So the first step to improving reliability of the hydrogen infrastructure is to have a vehicle that you know will do a planned route every day, filling up day in and day out, which of course lends itself beautifully to the refuse truck application and other similar duty cycles. After that, obviously, you want to be able to do it at scale so that you can reduce the cost and equally explore more appropriate hydrogen infrastructure technology. The data that I've just shown you, just further improving the NOx improvements, is replicated across the whole range of vehicles that we deploy. Every single one of the vehicles on that chart that you can see in front of you would have given anywhere between probably on average at least a 30% greenhouse gas CO2 reduction. but in the right duty cycle, we can further improve air quality as well. So although they're not zero emission, they're actually almost the best way available today under all the technologies, other than a direct electric vehicle that's not available for most of these applications, to reduce NOx emissions beyond the current standards. And we're just in the process of converting a fleet of refuse trucks, gritters for Glasgow City Council, that will become multi-purpose vehicles, the first of which is in the factory today. And this is where Glasgow City Council have understood the requirement to build up a base load of hydrogen vehicles and crack on with that before COP26 next November. So by the end of March, we will have had 20 vehicles through the factory converted and ready to be used and deployed in Glasgow as soon as the hydrogen refuelling is available. And in the next 12 months, we expect to do a further fleet of vehicles for Aberdeen. On your right-hand side is an example of a road sweeper that we've continued to do. Aberdeen currently have three vehicles converted. We're about to do another one that will be another manufacturer's sweeper. And the road sweeper application is again another classic example of an ideal way of employing day-to-day regular use through the infrastructure that's reliable and that can provide significant baseload. On the left-hand side, Merco with two 5 litre tanks installed on it, giving them 10 kilos worth of hydrogen, so that vehicle fills up every other day. Further to that, we can do RTICs. The vehicle you see in front of you would be ideally suited to do supermarket regional deliveries. It's slightly bigger, more capacity engine than they conventionally use, but the important point for RTICs is we need to have 4x2 engines, because otherwise there's not 4x2 chassis to ensure that there's space for the hydrogen, which is installed on the side. The alternative is to put the hydrogen behind the cab, which requires the fifth wheel to be further back on the vehicle to allow for the turning circle of the trailer. And in many instances, that probably makes it a bit challenging for the vehicle to be deployed. That vehicle that you can see in front of you is filling up at the Heathrow station and will do so daily on the route that's going to collect commercial waste. Just a small word, as I said, the focus that we can see that can provide baseload is to be on back to base locations. So in front of you are some examples. On the left hand side, the project that we did with Westminster City Council, Logan Energy supplied the hydrogen system, and you can see the footprint that's possible to do a small demonstration. Really doesn't need a lot of space to do a small site. Of course, that location will not be economic. It is not economic to do hydrogen at that scale, but it certainly allows you to have a demonstration project. And above you in the middle is a picture of a tube trailer, which is ultimately a way of having localized hydrogen storage delivered in on a hydrogen hub basis, as is the picture on the right, which was the station installed by Lindsay in 5. So in summary, it is arguably our case that today our technology is the only route that you could save carbon and deliver air quality benefits without a need to massively change your daily operation. It's not zero, but it is available now, and we contend that if we can get on the roadmap of building hydrogen infrastructure, then at some time in the future you might be able to convert to 100%. The reality is every day that we go past where we're not reducing our greenhouse gases, we are making the environmental impact of what we're doing continue to grow. I've tried to demonstrate that we can do a range of vehicles. The process involves us understanding duty cycle, use of the vehicle and finding space on board, and there will be a whole range around a location that will be possible. And as a consequence, it's a route to helping you maximise the hydrogen infrastructure use that will both be beneficial from a cost use basis and a reliability. and at the same time saving between 30 to 40% of CO2 across a fleet, as opposed to ones and twos that might be possible with either EV or fuel cell demonstrations today. That's me, thank you.
Thank you very much, Amanda. It has been an excellent presentation. I really have enjoyed that. I hope that all the audience have enjoyed as much as I have done. So let's go to the next speaker, coming from Alstom. Mike Maltum is responsible for leading and overseeing the innovation, business development, and sales activities of Alstom in the UK and Ireland. He also has the specific additional remit to promote and apply Alstom's hydrogen train technology in the UK market. So, Mike, all over to you, and thank you very much.
Thank you. Couple of quick questions first. Can you see my slides and can you hear me?
Yes, I do.
Good. Okay, so yeah, I'm going to talk about hydrogen in the rail sector. I represent Alstom, a company some of you may be familiar with, but many may not. Alstom is a global rail system supplier specializing in sustainable and smart mobility systems, typically around rail basis, and very much focused on how we can deliver more sustainable forms of transport than we currently have. So what we've heard so far this morning has been a very good introduction to the challenges that we face in the rail sector and every other sector of transport as we look to decarbonise. And I think what Amanda's just been talking about in terms of the challenges for HGVs, you need to consider those as an order of magnitude less than the scale of the rail infrastructure requirements and power requirements as we look at the types of consumption that we have. So as we go through this, I'll just explain where we are already. So Alstom has already developed the world's first hydrogen train. It is, as was discussed earlier, a fuel cell electric vehicle. It uses a PEM fuel cell with a battery in a hybrid drive system, and it was actually conceived initially in 2012. We unveiled it in 2016. It went into passenger service in Germany in 2018 and has covered over 180,000 kilometers in service in Germany before moving to the Netherlands, where it operated on a trial basis, and then a 3-month passenger operation in Austria that it has just completed. And so what we have there is very much the proof of the concept. The concept, like I say, emerged a long time ago. Alstom is also a producer of diesel trains, and I think it was fairly obvious even back in 2012 that we needed to move on from that technology. But why would we use hydrogen, and why do we want to do it here in the UK? And the drivers really are that we need a form of energy storage that we can carry on the trains to move those trains where we don't have electrification. We saw on Simon's graph earlier that the rail sector, if any of you noticed it, was the very line at the very bottom of transport emissions. It is the lowest emitting form of transport already, and per passenger is even better. But it's not perfect, and we do have still over 60% of the network by distance in Britain is not electrified and is operated by diesel trains. And we need to replace those. Now, some of them will be replaced by greater electrification. That's certainly one plan. But the government has set us a challenge to get all the diesel-only trains off the track by 2040. And that, whilst it may seem a long time away and is now further than perhaps the automotive sector is being given, that's quite a shift in terms of the investment necessary to either electrify railways or replace trains. Bearing in mind, trains have a 35-year life normally, so we're into all sorts of economic issues around early replacement if we're not careful. So what are we going to replace them with? We absolutely love hydrogen because diesel, because it's so energy effective. Its energy density per litre is very high, and as a fluid, a liquid, it's very easily stored on board a vehicle. Hydrogen gives us the next best thing. We actually operate or consider hydrogen to be for storage at 350 bar on board the trains, rather than 700 bar that is used in automotive. Commercial vehicles tend to operate at 350 bar, and in so doing, they have about an eighth of the energy density of diesel per unit volume, and are more than twice as effective as lithium-ion batteries. That's quite important. We touched on earlier the scale of a battery necessary. That hydrogen train I just showed you, the Hyster-Yale, our German engineers were calculating whether to power that by battery or by hydrogen. We didn't set out and say, let's do a hydrogen train. We set out to say, what's going to be the stored energy option replacement for diesel? And we calculated that the battery, irrespective of its electrical properties, or due to its electrical properties, I suppose, but it would weigh 33 tons per train. So in that terms, you've got all the charging issues that were highlighted in the earlier talk by Venkat, and you've also got this problem, fundamental problem of the mass of the battery. Hydrogen solves those problems to the best extent of any currently known technology. So we can store adequate energy on board the train to power it for a day, and we can carry the weight entailed in that on board the train, and combine it with a modest size of battery that doesn't involve all of those compromises that otherwise full battery power would bring us. And we can use that battery then to capture regenerative energy as we slow the vehicle and make it as efficient as any other form of hybrid opportunity. So that means what we have now, in order to achieve these objectives that the governments around the union have set us, is the option between really electrification of the railways and the use of hydrogen. And so they compete, but actually they can complement each other. And we'll be looking over the years to come at how the balance between electrification and stored energy will be deployed across the country to eliminate diesel. If you want to look at what can a hydrogen train do, so what does it need to do as well? So we really need it to have a range in excess of 1,000 kilometres, so that's sort of 600 miles upwards. We need it to do speeds of up to 100 miles an hour, and these are all performance that the Hyster-Yale achieves currently. We want zero emissions from the train. We'll use the battery for regen energy. So all of these things are proven and can be done. They fit the regional passenger service requirement, which is where the majority of diesel trains operate. Britain is very unusual in operating higher speed diesel trains over 100 miles an hour. And they are the most likely routes and the most appropriate routes to electrify. The more technical of you on the call will know the difficulties or the increase in energy requirements for higher speeds. And given that in rail we operate at speeds of up to 360 kilometres an hour in regular service, there are some very obvious candidates for electrification around the world. And even in the UK, we also have a very high electrical demand already from high speed, high intensity routes, and those are where electrification should be applied. It's interesting that Network Rail is actually the UK's single largest electricity customer. But looking at the regional passenger services, this is a real sweet spot for what hydrogen can do. And picking up on what Amanda was saying, it also fits very well with those issues around creating a baseload demand and allowing you to justify and bring along the appropriate infrastructure investment to support a fleet. Introducing a fleet doesn't mean you have any service impact. Electrifying a railway, of course, means you've got to close it periodically, every day, every night, whenever you do it, in order to fit the electrification. I should at this point declare an interest. Alstom provides electrification, as we do electric trains, hydrogen trains, battery trains, all of these technologies we have available. But we recognise that each of them have an appropriate application. The Hyster-Yale now, the first trains in operation, there were just a pair of them operating those trials and operations that I referred to earlier. We have 41 trains ordered for deployment in Germany. We've also recently signed a further order for a different type of hydrogen train to be deployed in Italy, and we're actively working with the French railways on a third type of train for their applications. So we're seeing already considerable interest in Europe and elsewhere around the world for this technology. What we're doing here in the UK is working with a company called Eversholt Rail, which owns fleets of existing trains, and we're going to look at converting electric trains as they currently are into what we call breeze hydrogen trains. The reason we're converting electric trains is that they are available, that we can shorten the development lead time and the costs overall, and that we can also deploy fleets over a slightly shorter period. If you have a 35-year life of a brand new train, it is a leasing market for trains. It's quite difficult to construct a business case around brand new trains right here today. That time will come very soon. But for our particular commercial market as it stands at the moment, we feel conversion is better, and we'll start with electric trains rather than diesel trains, because just at the moment there aren't diesel trains available to convert. It may seem perverse, but they are all in active service and they can't be removed from that service without reducing the scale of the operations they currently provide, which doesn't really solve the problem we're trying to solve. So collectively with Eversholt, we've invested significantly in developing this concept. I'm talking to you today from our facility in Widnes, where we are developing the design. We have a train now on site, which is being used for development purposes and further trials of the design concepts. And our objective is to deploy operational fleets into commercial passenger service. It's not about technical demonstrations or one-off trials. Those technical demonstrations, if you want a demonstration, you're very welcome to come to Germany and see our trains in operation. One-off trials don't create the backdrop for appropriate investment. They're not really something that help us progress. They can be appealing and conceptually lovely, but frankly, from the point of view of getting this technology deployed, we're not really moving forward with one-off trials. We want to see fleet deployments. We want to build that base load demand for the hydrogen, which then justifies the investment in the hydrogen production facility that the trains need. And where Amanda was explaining the potential demand from a 100 lorry fleet, I think you said, Amanda, 200 kilograms. For us, a 10 train fleet, which is about the optimum or the minimum scale of fleet we'd like to really deploy, you're talking at a requirement of 2 to 3 tons of hydrogen per day. So an order of magnitude larger, which means that the fueling facility is a very attractive proposition to a gas producer, and that as we deploy fleets around the country, we have the opportunity to create transport hubs and multimodal operations from fueling facilities of scale, which could then support further return to base operations such as taxis and buses, which link up to the rail service and bring to reality that holy grail of a door-to-door zero-emission journey opportunity for passengers without using their own individual vehicles, reducing congestion, reducing the overall number of vehicles that need to be produced, and as a whole, reducing the carbon load of our transport system. Like I say, the train will be called Breeze. It'll look similar to this. This is our concept livery. Every operator will, of course, apply their own livery. And we would expect these to be entered into service around the country wherever there is no proper prospect of electrification in the short to medium term, and where it makes total sense to start reducing carbon emissions as soon as possible. And as soon as possible for the first fleet would be around about 2024, starting today, and going forward, follow-on fleets could be introduced into service fairly rapidly, because we would be able to run a continuous production process from here in Widnes, delivering fleets around the country, matched in each location with an appropriate fueling facility. And we would expect most of those to be electrolyzer based, but we're talking megawatts of electrolyzers to achieve this. So quite large-scale production capability that goes with each train fleet. And like I say, that then builds up their network, which will become attractive to the development of brand new long-life hydrogen trains that will operate for decades to come. And thank you. That was what I wanted to talk about.
Thank you very much, Mike. It has been very, very excellent presentation and very exciting just to hear all about this new hydrogen applied to fuel cells.
Thanks for the introduction and good morning. I am Ryan Riley, Business Development Manager of MJR Power and Automation. MJR are headquarters in Teesside and have been delivering solutions and services to the marine and offshore sector for over 20 years. We are actively working with our clients in the decarbonisation of their operations and assets, both in at port and at sea. This morning we're going to look at the current and future trends for hydrogen as a fuel source for the maritime sector with application examples, barriers to adaptation and future implementations of the technology. So what is driving the need for decarbonisation of the UK and maritime sector? In 2016, domestic shipping, ships that start and end their journey in the UK, including overseas territories, accounted for 11% of the UK's total domestic nitrous oxide emissions and 7% of the sulphur dioxide emissions. From the graph, you can see the significance of meeting the targets set for net zero emissions as the impact it has on global warming. The UK, of course, does contribute to the global maritime greenhouse gases emissions, both through international shipping, calling at UK ports and UK domestic shipping. UK shipping accounted for 5.9 metric tonnes of CO2 equivalents in 2017. In 2016, it was agreed at the IMO that the North Sea would become a NOx emission control area. This would enter into force on the 1st of January 2021. Following on from the reduction of the SOx emissions to 0.5% in 2020, and will require new build ships delivered and after that date to operate against the IMO's Tier 3, which is the most stringent NOx control standards. In practical terms, this means that new ships operating in these waters will need to reduce their NOx emissions by around 3/4. This represents significant progress, and the industry has invested in new technologies like exhaust gas cleaning systems and LNG as a fuel in the short term. This is an overview of the UK ports, which comprise of 53 major ports in the UK and a further 108 minor ports. Together they account for 481.8 million tonnes of port traffic, in which 95% was handled at the major ports. The port sector is therefore extremely diverse and is characterised by some very large ports, which accounted for a substantial share of overall UK port traffic, along with some very small ports. With the expected increase in both traffic and increase in vessel size, the UK maritime is facing significant demand at the port for electrical, both driven by electrification of port operations and services and the decarbonisation of the marine sector through shore power, supplies and providing alternative fuels to meet the 2050 maritime targets for reduction in emissions at port and at sea. Another challenge for UK ports is existing network capacity to deliver the future demand, which can be supplied or supplemented by renewable resources generated either inland or offshore, with storage such as hydrogen and or battery technology. This diagram lays out the current and future alternative fuel systems and infrastructure for ships propulsion, shown with both onshore processes and ship-side requirements for low or zero emission propulsion systems. For the purpose of this presentation, we'll focus on the use of hydrogen as a fuel and the process for using the power, the ship propulsion and or hotel loads when near or in port. It is also worth noting the projected global market for UK supply, especially in the fuel production. It's estimated that in the UK could potentially generate 10,000 gigawatts from wind energy in its own waters by 2050, which is well above the figure of 1,000 gigawatts likely to be needed for the UK electricity demand, with additional generating capacity to produce low-cost, sustainable green hydrogen with zero emissions from water electrolysis, according to a recent report from the Offshore Wind Industry Council and the Offshore Renewable energy catapult. If we look further into the marine fuels and compare the zero carbon fuels from the previous diagram, we can see that hydrogen has a superior energy density in all forms compared with the current lithium battery technology, which is widely accepted for new builds and retrofits as a proven technology for reduction in emissions with hybrid electric systems. Lithium battery solution is only part of the answer and has limitations, especially for quick refueling and longer transit journeys. Looking at the carbon-based fuels, LNG systems has been seen as a viable option with additional scrubber systems to meet the NOx emissions. With LNG, bunkering and storage is not well available to ships at existing ports globally, which has resulted in slow uptake of that fuel. So if we look at these technologies and see how deployed in today's market, we can see the transition from the historic direct mechanical propulsion systems for your diesel engines to the more widely accepted hybrid propulsion system, which is diesel electric with battery storage. As we can see today in 2020, we have hydrogen fuel cells available as well as full electrical propulsion, which is suitable for some type of vessels and still in the early stages of development of other biofuels, including ammonia. If we consider a conventional hybrid propulsion system, we have a common DC bus with converters for the supply of power to the propulsion. The significant diesel engines used for transit speeds and with comparably small batteries used for manoeuvring in field or in at port. Whilst the vessel can operate at low power on batteries only, most of the propulsion power will come from the diesel engines at high speed power demand, using the batteries to optimise the diesel generators to the nearest and best efficiency point, approximately 8% load. So whilst near port and in-field operations can run 100% on batteries, the overall reduction in emissions through battery hybrid technology is limited, with the need for diesel engines to be produced for a high transit speeds. If we take that a stage further and look at the full electric system with backup/top-up diesel generators, then the reduction of emissions are significant, but the battery footprint and weight is not practical, especially for smaller vessels, for the space and additional weight requirements on the vessel. When it comes to charging, you need the ability to plug in when at port, and with electric charging, this can be a significant amount of time compared to conventional diesel or alternative fuels such as hydrogen fuel cells. For hydrogen fuel cells, the equipment architecture will remain the same, with the ability to connect the DC links through DC to DC converters, making it feasible for upgrade options. This particular single line diagram is for a crew transfer vessel which operate in and around wind farms, and we're currently working on a project for developing offshore charging solutions powered from wind turbines to have the ability to charge at sea, which makes future solutions more practical and viable. We have also considered hydro fuel cells in the basis of design. By using a similar architecture, we can incorporate hydrogen fuel cells and upgrade for the diesel engines in the transition to 100% zero emissions power for propulsion and auxiliary loads. Here are some current demonstrator projects for hydrogen propulsion on commercial vessels. On the left-hand side, the Waterground project in California. When launched in 2020-2021, the Waterground will be the first fuel cell vessel in the US and claimed to be the first commercial fuel cell ferry in the world. The vessel consists of two 300 kilowatt shaft motors, 100 kilowatt hour batteries in the hulls which provide boost power to achieve the 22 knot transit speed. The hydrogen tank array, which is a 264 kilograms, 250 bar compressed gas, which will give up to 2 hours full days fuel consumption. On the right is the High Seas 3 project, which is to demonstrate a commercial ferry using hydrogen derived from excess renewable energy resource through the electrolysis of water to produce green hydrogen for the ferry, and combined with the battery pack to deliver a zero emissions passenger car ferry, in addition In addition, the project will look at how the concept can be made commercially viable, including not just the vessel, but the local hydrogen production, storage and refuelling infrastructure. If we look at current developments in fuel cell operations, Bollard have recently launched their FC-Wave product to provide primary propulsion for power marine vessels, such as passenger and car ferries, rower boats and fishing boats, as well as stationary electrical power loads to support retail and auxiliary loads on cruise ships and other vessels while docked at port. They come in 200 kilowatt units and are scalable up to megawatt systems. They're currently engaged with DNV for approval, for type approval of this fuel cell module for use in ships and critical systems. They expect 30,000 hours life from the fuel cells, which equates to about 5 years of operation, and has a lightweight at 4.41 kilograms per kilowatt hour. Moving a bit into the future, we can see that the world's first liquid hydrogen fuel cell cruise ship is planned for 2023. This is a Norwegian project which is aimed to install 3.2 megawatts of hydrogen fuel cell onto a large cruise vessel, currently being designed by Hyster-Yale Design for the ship owner Havila in Norway, and integrated by NES with fuel cell supplied by PowerCell. This would be the largest fuel cell ever placed on a major ship, replacing the more frequently used compressed gas. Batteries are planned to store additional energy to make up the system fully emissions-free. The liquid hydrogen will be supplied from a bunkering vessel or truck, then stored aboard for the cruise ship in a liquid hydrogen tank. The vessel will be initially equipped with batteries and natural gas as a fuel, with planned retrofit by 2023, which will combine the 3.2 megawatt hydrogen fuel cell with the existing battery storage. If we again look a bit further into the future, the planned project for the Viking Energy Research vessel, which is to use ammonia to deliver 100% carbon-free power, which will be critical to vessels for travelling long distances. According to the project plans, ammonia will meet 60 to 70% of the power requirements on board for a test period of 1 year. Viking Energy will still be able to use LNG as a fuel, and the remaining power requirements will be met by the battery system. So this is the next stage of developing hydrogen and derived from ammonia for long-haul vessels. If we compare the zero carbon emission fuels against the diesel internal combustion engine in the table below, we can see that the batteries have a higher efficiency conversion, almost double that, but the energy density is very low, and long recharging times at present and lack of port infrastructure and standards for charging limit the use and deployment of battery technology. Hydrogen gas is on par with diesel engines, approximately 40 to 45% efficient, and we can quickly refueled, but currently higher capex and opex with the current fuel cell life, which is approximately 5 years, but there is a reduction on maintenance. Both these technologies have been successfully used and are in the short-term part of the transition to zero-emission vessels, especially for those with the short repeat sailings and a combination of both hydrogen and battery technology. Within the next 5 to 10 years, and with support of the development and deployment and cost reductions, hydrogen liquid, ammonia, both as a fuel cell with conversion to hydrogen, and internal combustion engine technologies can be the answer to providing zero-emission shipping for larger vessels and longer voyages. The main challenges with all clean energy and zero-emission fuels is the same: capex costs against traditional diesel combustion engines, port infrastructure for refuelling, i.e. shore power and bunkering, and legislation and funding to fast-track the decarbonisation of the maritime sector with currently available and proven technologies and future developments. There are recent projects that will reduce the cost of hydrogen to make it more attractive as a fuel for marine and applications, but it needs to be done to adopt these technologies and build the support infrastructure. One thing I've not touched on is the benefits of going to zero emissions and low carbon technologies. There's a noise when it's in port. There's a low or zero noise pollution from that. There's a reduced maintenance cost. There's less running hours on the existing engines. It's derived from, or can be derived from, renewable energy sources, and there's incentives at the moment to change to low carbon technologies. In summary, in future, there will be many different types of fuel and energy generation which will be used to meet the 2050 targets for hybrid and propulsion systems, with hydrogen playing a major part in alternative fuels for zero emissions. In the UK, we both have abundance of renewable energy resource and the expertise to deliver on the decarbonisation targets, both inland and at sea, by integrating various energy resources and technologies to drive the zero-emission transport maritime sector. Thank you.
What are the challenges the business are going to have in the process of adopting hydrogen? I think this was directed towards ULEMCo.
Well, the reality is it requires capital investment to get hydrogen infrastructure in place. As Mike has explained for trains, and I've explained, the existing infrastructure for supplying hydrogen is critical. If I was a fleet operator considering CO2 reduction through hydrogen is important, I would therefore want to collaborate locally in order to be able to understand what both the public sector or other industrial users in my area were keen of doing, so that we can end up sharing the cost of the hydrogen infrastructure. Alternatively, I would need to look at my fleet and recognise that for the case of a slight disruption of some daily filling, I could deliver the CO2 reduction. But in principle, that's the main issue for certainly the customers we talk to, is where would they get the hydrogen from in order to take advantage of the technology. Clearly, the technology is at a stage where we can provide evidence and support of safe use. Some businesses would obviously need to go through a localised hazard assessment if you're going to install any change of use or fuel use on site. You obviously need to do a safety assessment to make sure that that's done. There's plenty of examples and case studies that can help to do that. So actually, other than that, in our technology, where the maintenance is the same as a diesel vehicle, once you've got the tanks employed, they'll probably have a life longer than the vehicle they're employed on. That's the main issues. I think the only other one our customers have, because we're doing a post-registration conversion, we provide a warranty to match the warranty that the OEMs provide for any of the parts that we might affect, which ultimately includes the engine and possibly the emission control. So that's the way we make that happen. Hopefully that answers the question.
Thank you. Would anybody else like to come in as well from the panel about that?
I mean, I can say from the rail perspective, it's a very different market, of course. We're in a highly regulated and market, which is very much government-led. And so from that point of view, as I mentioned in my presentation, the government has set a number of challenges. It then needs to authorise initiatives to go forward in order then to ensure that they get funded and progress to actual service introduction. So it's a slightly different process there, sort of less direct, commercial in the most obvious sense, but more partly political and partly policy-led process.
Okay. And Simon, is there anything you want to add from an investment perspective?
So, from a business investment perspective in hydrogen, I mean, I think infrastructure, just backing up Amanda's point, is a really, really key thing for whatever you're going to do, whatever the end use case is, how you get that hydrogen. And you need to get that hydrogen from a clean source for it to be effective from a carbon reductions point of view. And it all needs to be joined up. So the rail guys need to be speaking to the HGV guys, etc., to get some economies of scale. And I think that's if we had to do one thing in the UK, there's a lot of stuff going on within the hydrogen space. And until we join everything up, we will struggle to decarbonise and commercialise it.
If I might add a point to that as well, I think we do have an approach that tends to want to try and build a supply chain before there's a demand. What's crucial is to create the top end demand. If we start building hydrogen trains, we need lots of parts for hydrogen trains. Amanda needs parts for her trucks. All of us need that supply chain to support us. You can't build a supply chain without demand, and that has to come top down. And I think that's my point really about policy driven process. We need behind the statements we're all hearing at the moment and all of the government's enthusiasm for the technologies and for climate action, we desperately need to see actual commitments to projects. It won't take us further on its own. You've got to commercialise in order to secure an advantage. And once we've got a supply chain supplying us here in Britain, we can start exporting with that supply chain as well, and we can position ourselves globally much more strongly. Otherwise we'll end up as importers, just like we are for batteries.
Yeah, I think that's a really good point. And at the moment, we do import a lot of hydrogen tech, and we're talking about storage tanks or fuel cells or whatever you want to talk about. We do tend to import that more than not at the moment, and we need to pick our area. And it doesn't have to be the whole supply chain piece, but it needs to be some of those key components. And we need to provide support to those businesses who are developing those components.
Okay, thank you, Simon. I've got another question that's come through here. As a business, what incentives should be available to drive the transition period of hydrogen as a fuel? Amanda, would you like probably start? Probably a good line for you.
Sorry, could you ask the question again?
Yeah, sorry. So as a business, what incentives should be available to drive the transition period of hydrogen as a fuel?
Oh, that's very good. So in truth, I think today the business themselves need to want to make a change. Okay, they need to want to transform, because in truth, the most cost competitive way to deliver goods or do journeys in HGVs is to use diesel Euro 6 vehicles. So from an air quality perspective, they're very good, and they carry on as they go. So without a business incentive to reduce CO2 emissions today, then what I tend to see is companies will make very good verbal commitments to wanting to deliver net carbon zero, etc., but they actually tend to be doing that on how might I go about doing it rather than actually doing it today. So there needs to be an incentive, a genuine incentive, because in truth, the cheapest way to do what they do today is diesel. So the bosses need to accept that the business needs to drive in that direction. I think separate to that, beyond that, if and our technology provides a route where if you can put sufficient vehicles around a back to base location, the hydrogen itself can be priced competitive to diesel. That actually needs a volume and a capital investment, but it can be competitive to diesel. So here's an opportunity: you can reduce CO2 emissions and not cost yourself more than you currently pay for diesel. That's the possibility. Okay, If the business believes that they need to save money as well as doing a CO2 reduction, then they perhaps need to consider whether or not they are in the right perspective, because there is, once you take capex and opex into account, the cheapest way to run your operation is to do it with diesel. However, there are opportunities where if you set up that hydrogen infrastructure properly, the government has provided incentives such as the renewable transport fuel obligation that can help to reduce the initial capital outlay. If you collaborate with other people in your local area to ensure that the capital investment is spread over the significant volume, you can all gain the benefit. And in those circumstances, in the future, there are examples where actually using hydrogen will be cheaper than diesel, but that's because you've gone with volume and you've taken access through to the kind of big scale projects that are starting to happen. So, answer to your question, I hope that the incentive needs to be that people want to actually start on the roadmap to delivering CO2, recognising that we're in the start of that. If the government or policymakers could do anything to complement that requirement to help drive demand, as Mike has said, to drive demand and make it actually happen, so that if we invest in scaled production, there's actually places we can use it, then those things will help to create the market.
Just to add to that, I think, is it picking me up? Yeah, I think that we've got a situation in the automotive sector. The only reason we're not still driving around on leaded petrol is because of incremental changes to legislation over time, and the automotive sector moves in response to legislative imperative. They have to do it or they can't sell their cars. That is one way of driving the innovation on the part of us, the manufacturers. Managers talked about end users wanting it, but the government also does subsidise both the use of alternative fuels, but also the use of fossil fuels. And it needs to take a close look at how those subsidies work. So we have the renewable transport fuels obligation and the various complexities of that preclude certain types of vehicle and certain types of fuel as much as they encourage them. Particularly in the case of rail, it doesn't apply. And also we have situations where the diesel trains that hydrogen trains will have to compete with actually receive a duty rebate on the diesel. So the diesel is incredibly cheap. So yes, the standard mode of operation will always be cheaper. It's easy to say, well, just stop giving that subsidy, stop giving that rebate, but then you fundamentally undermine the cost models and the business models that have been used to operate the industry for many years. The same applies in the bus industry, incidentally. So you have to do it gently and slowly in terms of shifting the financial emphasis. But it is in that area that government can make improvements and changes, and small changes across huge fleets yield a lot of revenue that can be invested in the right channels. And I think there's definitely opportunity there. I'd also like to apologise to everyone. I do need to leave the call now, unfortunately. I think we were scheduled to finish at 11:30 and I need to go. So my apologies for that. That'll be my final contribution.
Yeah, thank you, Mike. Thank you for your contribution today. Thank you. Simon, is there anything that you want to sort of add at all?
Yeah, no, definitely on this, but I think it's an interesting point. I think, to put it bluntly, we need to increase the cost of diesel and other fossil fuels within the transport arena. The point about rebates on diesel within bus and train sector is very real, and I've previously spoken to operators who've actually said, oh, we'd love to do this, but we're getting paid. I mean, in the bus world, you used to get paid £40,000 a year to run your diesel vehicle, and I think it was about £4,000 to run a zero emission option. That was kind of rebates you got. So it needs to be, diesel needs to be more expensive, because then that basically allows hydrogen, electric, a combination of hydrogen and electric, to naturally become the cheaper options from a total cost of ownership point of view. And the other point is that I think regarding hydrogen and electric, they need to work together, and they often do very well. So one way of actually decreasing the cost of hydrogen, it can be, is you have a mixture of, say, some battery, which does a slightly different job, and some hydrogen on board. And the battery, although it has a high capital upfront cost, does mean you need less fuel, and electricity is very cheap, so it can provide some balancing for those total cost of ownership models.
Okay, thank you. I have another question that's come through here, just looking. I think this might be directed to you actually, Simon. What are the main challenges you anticipate for the government to orchestrate all infrastructure requirements and cope with demand?
Sorry, so repeat that question again, please.
Yeah. What are the main challenges you anticipate for the government to orchestrate all infrastructure requirements and cope with demand?
Oh, that's probably a question for someone in government. That sounds like a question for someone in government to me. That's a hard question because it depends on what we do. But obviously, the government set out their strategies they made a statement that we got to reduce greenhouse gas emissions by 2030 by 68% since 1990 levels. Transport's got, as I mentioned earlier, a long way to go to reach that target. Seeing as though, so between 1990 and 2018, we only reduced it by 3%. So we need to do something, I would suggest, a bit more drastic within the transport arena, and there needs to be money to support that, probably capital money to support some of that investment in infrastructure where required. There also needs to be planning and regulation. So it's not just about chucking money at this. We need to, from a wider perspective, think about electric cars, think about your house. If you've got a terraced house, it makes it much harder to have an electric car because how can you potentially charge it? If you had owned that space in front of your house, then you could always park there and you might be able to charge it all the time. That is a planning thing, and there's obviously some stuff around how you sell your house and the ownership of that car space. But there's a load of planning and regulation which we need to do, we need to put into action, and I think you need to not be afraid about whether it's a popular decision from a voting perspective. We need to just go out there and do it.
Thank you, Simon. Is there anybody else? I see Venkat's joined. Anybody else have anything to say, answer to the question? Okay, it looks like we've run out of questions then. So I just want to say thank you very much to all the presenters today. We, as Ruben's mentioned, we have another series of events going on throughout the next year, and I ask everybody to please keep an eye out to what the project is doing in Teesside University, and we hopefully look forward to inviting you and joining another event in the future. Thank you very much for your time today.